Welcome to Opening the Shutter on Snapshots. My name is Zach Klippenstein. I am a software engineer at Google. I work on Jetpack Compose. So just to get started here, this is going to be a pretty low-level talk. If you're looking for more of an introduction to Compose and a higher-level overview, recommend, if you didn't see Hitchhiker's Guide to Compose yesterday, checking out using Compose runtime to create a library later today. If you're watching the recording, feel free to pause and go watch one of those first if you want to. But that said, you don't need to know anything in this talk to use Compose. This is just really a deep dive. So this talk is ideal if you've used Compose a little bit and you kind of know what snapshots are, but it all kind of feels a little bit magic. So my goal here is to convince you that they're not magic, actually, and give you enough context to be able to read through the implementation code and kind of know what's going on. Lastly, I'm not sure if I'll have time for questions at the end, so I'd love to talk about this more. If you do have questions, feel free to reach out on Twitter or find me after this talk. I'll be around hopefully till the end of the day. So we're going to talk all about snapshots today. What do we need them for? What do they actually do? How do they do it? And maybe some cool things that we can do with them. But before we get into snapshots, I want to talk about files. Imagine that you're collaborating with your team, but instead of using version control, you're all just editing files directly on a file server somewhere. You're all just saving directly into the files, and you're probably going to have a lot of conflicts. See this message a lot. It would be really impossible to get anything done this way. And so we built some tools that help with this. Git is one that you might have used. It lets you do a lot of helpful stuff. You can capture the state of the code base before you start working on stuff. You can edit your files without worrying about changes from other people coming in during that time, even over multiple days. And when you're done with your changes, you can either decide to merge them and deal with any conflicts that come up, or just throw them away and pretend like they never happened. So snapshots are Git for your variables, more or less. With the Git metaphor, so layout, things like layout drawing passes, event handlers are like the programmers that you're collaborating with. And snapshots let you capture the state of your program at a point in time, change that state without worrying about other changes coming in. And when you're ready, you can either apply those changes or throw them away. So continuing this metaphor maybe a little bit too far, the reason we need this is composition is kind of like the release manager. Composition needs to be able to see a consistent view of the state of your program while it's running, and not have that changed by other threads or whatever while it's doing that. And snapshots help with that. So there's other parallels between Git and snapshots. Where Git has branches, snapshots are basically branches. Git has a main branch, snapshots have a global snapshot that's always open and it's always there. And it's the parent of every snapshot. Git has commits, snapshots have state object rights. You can merge branches in Git, you can apply snapshots. There's a way to resolve conflicts with snapshots called merge records that I'll get into later. And Git has hooks, and you can listen for changes to state with snapshots with various observers. So there's a word for this in databases, some of these features. It's called ACID. It stands for atomicity, which means that when you make a bunch of changes, they'll be seen by everything else all at the same time. Consistency kind of means two things here. So when you take a snapshot or create a branch in Git, you kind of capture the state of the world, and then you know that nothing's going to change out from under you while you're working on that snapshot or on that branch. It also means that when you apply changes that you've made, they'll either all apply, or if there's a merge conflict, they'll not apply together. You won't get partial application. And isolation means that when two different snapshots or branches are making changes at the same time, they won't see those changes, and they'll be isolated from each other. And the last letter, D, stands for durability, which means that changes get persisted. But snapshots are in-memory systems, so they don't have durability. So you can think of snapshots as providing ACID without the D. And they also resemble databases in other ways. Databases have transactions, and snapshots are kind of like transactions. You can commit and roll back transactions, and you can apply and dispose your snapshots. And where you've got views of data in databases, derived state, which you might have seen a derived state of, is kind of similar to that with snapshots. So this is cool, but how do they actually do this? Well, it's not magic. Although I don't know, it feels like it, which is really cool. Maybe it uses a compiler plugin. Compose has one of those, I think. But it's not that either. And in fact, snapshots are really a separate library within Compose. And it's actually a pretty small library. It's only like a few files, really. And Compose is built on top of snapshots, and they're very fundamental to how Compose works. As I said earlier, composition relies on some snapshot behavior, and of course, observing changes is how you trigger recomposition. But you can use snapshots without using anything else in Compose, without using the compiler plugin or the rest of the runtime. And so snapshots themselves are built on, again, not magic, just standard programming stuff. Linked lists, integers, ThreadLocals. So if we're going to try to imagine how we might build something like this, we might start with a giant state container like Redux uses, where every snapshot is going to just have all of the state in your program. And every time you want to make a change, you have to copy the container over, change something. This could potentially use a lot of memory and take a lot of work to do all this copying. Imagine if you're like animating something and you're making all these copies. It's also the API is also not super great. If you've used something that uses Redux, you probably have there's probably a whole framework you have to plug into to give you access to that state. But we'd really like to just use Kotlin the way we normally would write code. So snapshots actually work more like this. Instead of putting the state in the snapshots, each of the state objects has all of the data for all the snapshots that care about it. The snapshots themselves are just metadata. And very important to note that snapshots don't contain any pointers to state. They don't really know about each other except kind of indirectly. So the arrows here, well, there's no arrows on this side. The lines indicate which values inside of the state objects on the right those snapshots would see. And so let's look at an actual example. We call these rows, by the way, records. One other thing to note is that because of this, snapshots and records have a many-to-one relationship. A lot of snapshots can see, and often will see, a single record in a state object. And in fact, when you create a new snapshot, it will initially only see existing records. Writes, on the other hand, have a one-to-one relationship. When a snapshot does a write, it needs to have its own record to write into. And we'll talk about how those get created in a bit. So some other comparisons. Snapshots are a relatively lower level API. You probably, if you've used Compose, you probably haven't actually had to use snapshot APIs directly, but you've probably just created state objects. Mutable state of and friends are the main API into this system. Snapshots are concrete objects that have some well-defined data. They have an ID. Every snapshot has a unique ID. They also have the history of the previous IDs that snapshot has had, and a set of invalid IDs. And I'll talk more about why those are needed in a bit. State objects, on the other hand, the state object class, or interface actually, is it's an interface. It's totally abstract. And you can make your own state objects, and they can be whatever, but they do have to have a map of these snapshot IDs to the records that were written by those snapshots. In terms of API, snapshots, you might have seen maybe with mutable snapshot here, but a lot of these are, again, lower level. Compose is going to use these, the Compose runtime for Compose UI and stuff is going to use these internally, but you won't have to touch them yourself typically. State objects, on the other hand, mutable state list of, mutable state map of, and mutable state of are the three state objects that ship with Compose. Again, you can create your own, but these are the three that it comes with. And if we're going to look at what they can do, state objects are pretty simple. You can read from them and write to them. When you read, the state object will look for the record that it needs to read from and then read from it. And writing is similar. It'll find the record to write into or create one if necessary, and then write into it. Snapshots have a few more operations. You can create them when you create a new snapshot, it gets a new ID. You can enter the snapshot, which means you're now running code in that context of that snapshot. And the way that works is it sets a thread local when you enter, and then it restores the old snapshot thread local when you leave. That's how you can access snapshots without having to actually pass them around anywhere. And you can apply a snapshot, which means that the snapshot's ID is going to be marked as committed and part of the canonical state, at least for the parent, and it'll notify listeners that stuff has changed. So, OK, now let's look at an example to make this a little bit less abstract. We've got 3 snapshots on the left with the ID on the left and the snapshot's invalid list on the right. And then we've got 2 state objects here, message and color. And each of these state objects has a number of records. So let's start by looking at snapshot 80. If we're in snapshot 80 and we look at the value of message, we're going to see just HE. It's going to look for the record in this state object that has an ID that's less than or equal to 80. So we would find 72, but 72 is in its invalid set, so it's going to skip over it. And that's just all the invalid set is, a list of snapshot IDs to skip. So it's going to find 25. If we look at color, we're going to find 80 because it matches exactly. If we look at snapshot 91, it's going to read message, it's going to find 84 because it's less than 91. And if we look at color, it's going to see 25 because it would find 80, but it's in the invalid set. Lastly, snapshot 72, it's going to see hello in message. And a cool thing is that because the IDs match directly, you know that snapshot 72 here actually wrote that value into that record. If it looks at color, it's going to also see red. So the way that this actually works, it's a pretty simple rule. When a state object looks for the record for a given snapshot, it's just going to look for the newest valid record, the highest ID, like I said, that's less than or equal to the snapshot's ID, and it's not in the invalid set or the record's marked invalid. And in this example here, the hello world or hello ASDF has no ID, and so that one is kind of like tombstoned. So that's the rule that we use to find records. But what about the snapshot IDs? Where do these come from? So going back to the Git metaphor, once again, in Git you have commit SHAs. Snapshots use a monotonically increasing ID counter. So every new snapshot gets the next highest ID. This means that snapshot IDs are really kind of act as a clock that represent the order in which snapshots were created. So a lot of the tricks for how snapshots work are in how these IDs are assigned. So let's look at some examples. We're going to start with a pretty straightforward one. We're going to create a state, take a snapshot, write a new value into that state inside the snapshot, and then apply the snapshot. On the left here, I've kind of got like a branching style diagram, which I'll keep around as we walk through. And let's get into it. So first thing we're going to do, start in the global snapshot. And we're going to give it ID 0 because it's the first one. So we're going to write the initial value into the message state, which is going to create a new record with ID 0. And that's it. Now we're going to take a snapshot. So we're going to create a new snapshot, give it the next highest ID. And it's going to point to, or it's going to select. Again, there's snapshots don't actually point to records. They just like act as queries into the state objects. So snapshot is going to select the first record from the message state object. But creating a snapshot is actually a multi-stage process. So the first thing we do is we assign it the new ID. Then we have to advance the parent. And advancing means we're going to give it a new ID. So again, we're going to look at the counter, give it the next highest ID. And then we're going to save the old ID in the list of previous IDs. Then we're going to take the difference between the old ID and the new one, and that range, we're going to add it to that snapshot's invalid set. In this case, it's exclusive range. So in this case, that's only ID 1, which also happens to be the ID of the child. And this is what allows the parent to, or allows the child to make new records and do writes, and the parent won't see them yet. because 1 is less than 2. Notice that we haven't touched the state object at all after we wrote that initial value. Creating this snapshot was just touching the snapshot metadata. So now we're going to have snapshot write into message. So it's going to have to create a new record to have its ID. It's going to write its new value in there. And so now message has both the initial value and the end hello in separate records. And that's it. That's writing is pretty straightforward. And we don't have to touch the snapshots at all to write this in. We just touch the state object. Now let's apply the snapshot. The first thing we're going to do is move the ID to the parent's history. You can kind of think of it as the parent absorbs or becomes the child. Then we have to remove that ID from the invalid set, which is what actually allows the parent to see that write. And this is kind of the change that actually applies the writes. As soon as that ID is removed, in this case we just have the one state object, but any state objects that were written to by that snapshot will now be visible to the parent. 1 is less than 2, and it's not in the invalid set. Then we have to advance the parent again. We do a lot of advancing, and then we're done. So there's kind of 3 main rules here: creating a child, applying a child, and advancing. And these are the steps that we kind of walk through. I'll have this slide here as a reference, but we just went through it, and I'll go through a few more examples to make this a little bit more interesting. So let's create 2 state objects now, and take 2 snapshots, and then have each snapshot change a different state object. So we're going to start again in the global snapshot, write some initial values, create a child. This is similar to the previous one. We just have 2 state objects now. Advance the parent, update the invalid set, and that's it. Now we're going to create the second child and go through the same set of steps. Create the child. We're also going to, this time, copy the parent's invalid set into the child. And this is important because it allows snapshot B to ignore snapshot A's writes. Because 3 is greater than 1, 3 would normally see records with ID 1, but because 1 is explicitly excluded, it'll skip them. Then we advance the parent one more time and add the new ID to the invalid set. And now the global snapshot will ignore both snapshot A and snapshot B for now. So now we're going to write into message from snapshot A, and then we're going to write into color from snapshot B. So they both create new records with their respective IDs and write into those records. Let's apply snapshot A. This is the same process as we did in the previous walkthrough. We're going to move the ID into the parent's history, remove it from the invalid set, which now allows the global snapshot to see hello. And then we have to advance the parent. And because now 5 is greater than 3, but it still won't see any writes from snapshot B because 3 is in the invalid set. So now let's apply B. We're going to do the same set of steps, move the ID into the parent's history, remove the ID from the invalid set, so now the global snapshot will see writes that snapshot B did. In this case, it's color. And then we advance the parent. So these rules work with any number of children, and they also work with any number of grandchildren or nested snapshots. The same basic rules will work with any depth or breadth of tree inductively. So there's nothing special about the case where you have multiple snapshots. It's just the same set of rules. But just to really illustrate that even clearer, let's do a nesting case. So we're going to have 2 states again. We're going to create one snapshot, write to one of the states, and then we're going to create a nested snapshot and write to the different state, and then apply them inside out. Start again, global snapshot, write both of the initial values, create the first child, advance the parent, update the invalid set. Then we're going to write from snapshot A into message. Now it gets interesting. We're going to create a child snapshot of snapshot A. It's also going to select the same initial records. And although you might wonder, OK, so 3 is greater than 1, why isn't it seeing hello? Well, That slide is actually wrong. It would see hello. So we're going to, in this case, because we advanced snapshot A, we're going to take the difference between 1 and 4, so that's 2 and 3, add that to the invalid set of snapshot A. And now snapshot A will not see parent rights or any of its child's rights. We're going to write from snapshot B into color. Now we'll apply snapshot B, add the ID to the parent's history, remove it from the invalid set so that snapshot A will now see that right. Advance snapshot A. And now we can apply snapshot A. Same set of rules. We move the current and all of the previous IDs into the previous list of the global snapshot. Remove the IDs from the invalid set. And now we have to do one more thing, which is advance the global snapshot, which allows it to see the other right as well. So again, same set of rules, and works with nesting as well as multiple sibling snapshots. So that's how snapshot IDs work. I've talked a lot about state objects and records, but how do those actually look in code? Well, we've got a mutable state type, so when you call mutable state of, we get a mutable state. So let's see what that looks like. It's an interface. It has a value property and some other stuff that we will ignore because it's just calling sugar. So what implements mutable state? Well, there's another interface we have to look at first, snapshot mutable state, which adds this policy thing that we'll see in a second. And then finally, we have a concrete implementation, snapshot mutable state impl. So this is an internal class, and when you call mutable state of, it returns one of these. It's got the value property with some getters and setters, and an initial value. But notice it also implements a second interface, state object. The state object interface is what actually is what the snapshot system actually uses to make this whole thing work. So the list of records inside of a state object are actually stored as a linked list. And this first state record property points to the head of the list. The prepend state record function allows the system to insert new records. And this merge records function is optional. It's got a default implementation. But when the system detects a conflict where two snapshots change right to the same object, and then both try to apply, it'll call this function to try to give you a chance to resolve them. So this is just like resolving a Git conflict. You've got the shared kind of common base commit, and then you've got your changes and the other changes that you're conflicting with. OK. So back to snapshot state mutable impl. Let's add the required stuff from state object and actually implement this. So we need a record to actually store the data. So we're going to create this private class state record. That's exactly what it's called in the code. And it's going to take an initial value, put that in its value property, and it also subclasses this state record class. This means that there's two other methods we have to implement: create, which is going to just create a new basically just a new instance of state record, and it's a factory, and assign, which allows us to assign one record to another. And so if you have a custom record with a whole bunch of data in it, you can copy over all your fields here. Next, we need to store this somewhere. So we're going to create a private property that's a var, it's mutable. And we're going to just create a default one in there with our initial value. And then we need to return that from first state record and set it from prepend state record. And that's all we have to do to get this linked list. The way this works is that state record, the abstract class, has a bunch of internal properties that the snapshot system will actually use to link records to each other. And so all you have to do is remember what the head of the list is and update it as asked. So the last thing we have to do is actually return some data from value. So we could just look at next, the only record that we have a reference to, and get its value. But remember the rules we talked about earlier. We need to find the record that's appropriate for the current snapshot. And it's really easy to do that, actually. We just call this extension function readable. And that's an extension function defined on state record. And it'll just basically read the snapshot thread local, find the appropriate record, and return it. Setting the value is similar. There's a writable extension function that we call, and then we pass it a lambda, which will get the record. And so when you call writable, it'll look at the current snapshot. It'll try to find a record that matches the snapshot ID exactly. If it can't find one, it's going to use that create or assign methods on the state record that we defined to either reuse an old record or create a new one, and then pass it to this lambda. And then we can just update whatever fields we need to in there. So that's basically it for the basic implementation. But we still have this policy thing. So that's actually used to implement this merge records method. And the way this works in mutable state is the policy, the snapshot mutation policy, has two features. It can check if two records are equivalent, and it can merge the records. So when the snapshot system detects a conflict, it's going to call merge records. Mutable state is going to ask the policy if the records look like they're the same. So if you've ever passed in mutable state of with never equals or a custom policy, that's what it's doing, is it's asking this equivalent method if the records are the same. Never equals, well, return false from this all the time. If they're equivalent, there's no conflicts. So resolving them is trivial. We can just return one of the records. Otherwise, we have to resolve the conflict somehow. So we're going to delegate to the policy's merge function, and it's got kind of the same behavior as this one, just with the actual value inside the state object. And if it returns a valid value, we're going to create a new record, store the value in there, and return it. If it returns null, it means the conflict couldn't be resolved. And this is a default implementation. And it will just return null to indicate that to the snapshot system. And then the application will fail. So that's basically how mutable state works. So that's basically the important parts kind of the snapshot system that I wanted to talk about. Now let's look at some other cool things we can do. We just looked at an implementation of a state object. So let's look at making a custom one. Let's say we've got this range here. It's just an integer range, and it's mutable, so you can change start and end. Let's turn this into, let's make it snapshot aware. So we're going to implement it in the kind of very similar way as mutable state. We're going to give it a record type, create a assign. In this case, we've got two properties, so we're going to assign both of those. Then we're going to implement the start and end properties using the readable and writable extensions. And the first state record and prepend state records to update the list. So this is the same set of steps as we did for mutable state. Now we're going to add some new functionality. Let's validate the start and end values so that you can't make start greater than end. We're going to do that in the setters first. So we're going to call Kotlin's require function, and we need some way to get the current value. So, well, maybe we could use this readable extension again and check if the new value is less than or equal to the current value's end. But this doesn't actually work very well because another thing that the readable and writable extensions do is report to the snapshot observers that a value was read or written. So when you change a value in an event handler, for example, the way that Compose knows to invalidate composition is because it was listening to reads the last time you did the composition, and it saw that you read something. And when that changes, it needs to schedule a new composition. But if you're just writing a value, that's not a read, so you don't want to have to do that. So if we use readable in the setter, it's going to trigger more updates than it needs to. There's another way we can do this. It's called with current. And it's basically just readable, but without reporting the read. So it still selects, it gets the snapshot thread local, selects the right record, and passes it to this lambda. And The reason this is a lambda instead of a return value, I think, is just a convenience thing. So this is kind of like the with function. It returns whatever value that lambda returns. In this case, all we need to do, though, is run this require function. So we do that, and that's it. We can also, that's not it for validation, though. So now we validate when we set a new start or end value. But it's possible to, in two snapshots, have two valid ranges, or versions of the same range that are both valid. But then when we apply them, the start and end get out of sync. So we also have to validate when there's a conflict. So we're going to start in a similar way to mutable state. The first thing we're going to do is check if there's actually a conflict. So if the records start and end match, then there's no conflict. We can just return the first value. Then we're going to look at which snapshots changed which property. If both snapshots changed start or both snapshots changed end, then that's an actual conflict, and we don't know which one to choose, so we're just going to return that it was we couldn't resolve anything. The only case where we can actually successfully resolve the conflicts is if one snapshot changed start and another snapshot changed end. And so we check that here. We take the newest start and end values and put them into a new record and return that. And that's our merge function. So this is a kind of one example of a custom state object. There's other things you can do with this. You can take basically any mutable data structure and make it snapshot aware and play with it and see what you can do. Another thing we can do with snapshots is kind of diffing state. So here's basically a Hack Week project I did a couple of months ago. I wanted to see if I could kind of replicate the with animation API from SwiftUI. And the way this works is when you want to change some state, if you want to animate that state change, you just call with animation, takes a lambda, and you make the state change within that lambda. And then it magically, automatically animates it. So I have a demo here in the GitHub repo. This code, it's not I didn't publish it on Maven because it's just kind of very hacky. But if you want to take a look at the code, it's there. But I'm going to run through a bit of a simplified example just to show how this works. So we're going to start with the suspend function because it's animating, and in Compose, animations are done with coroutines. Then we're going to take a mutable snapshot. So in this case, it's probably going to take this mutable snapshot is probably going to be a child of the global snapshot, like we saw in the other walkthroughs. And it's going to, so take mutable snapshot takes two optional parameters, a read observer and a write observer. And those are just functions which will get called whenever you read from or write to a state object. So here we're going to pass a write observer that's just going to remember every object that gets written to in this set. Then we're going to enter the snapshot and run the function. As changes is running, that write observer will get called every time a state object gets changed. After changes returns, we're going to look at all the objects that were changed, and we're going to read their new values. Because we're still in the snapshot here in this for each, when we read state object.value, that'll be the current or the new value of that state object that change is assigned. Then we're just going to throw the snapshot away. We don't actually care. Because that snapshot, because we made those changes in a snapshot, no other part of the program will have seen them. And then we dispose it, so it'll be like we never called changes in the first place. And this is cool because we need to run changes to get the set of things that changed and to see what the new values are. But now we want to animate them over time, so we don't want to apply them right away. To do the animations, we just create a coroutine scope, loop over each of the changed objects, and then launch a coroutine to animate. Here we read the state object value again, but because we're outside of that snapshot, we'll now see the old value. So we can use that as the initial value for the animation. And then we look at the target value that we saved from inside the snapshot and use that as the target. So this is a simplified version of the implementation. There's some extra stuff to work with types in the real code, but this is basically how it works. Yeah, this is on GitHub, so you can take a look. A third thing we can do, and this is, I don't know if this actually works, but we said snapshots provide asset without the D. Maybe we can implement the D. So one way we could maybe do this is wrap like a database, like a Broom or SQLite. We could vend like queries from the database as state objects, and then use something called an apply listener to see when those state objects are changed and save them back into the database. So I haven't actually tried writing this, or running it at least. I don't know if this would work in practice, and I'm really curious, but just kind of as a sketch of how this might work, we could create, let's say we've got the user and user DAO examples from the room docs. We're going to create a class that's going to query for a user by name, return it as a state. So the way we could write this is maybe we have some cache of state objects, so we don't create a whole bunch. If we don't have a cache for the current user, we're going to ask room for a observable flow for that user record. And then we're going to just launch a coroutine to collect that one and update the state value and add it to the cache. And then we can return that state value, and any code reading that state will just see the new value as it gets updated in the database. The more interesting part, in my opinion, is how we detect changes and update them. So we're going to call snapshot.registerApplyObserver. And this is it takes a function that gets the set of changed state objects. So when a snapshot is applied to the global snapshot, this callback will get invoked. It'll get the set of everything that changed and the global snapshot in which those changes are visible. So we're going to look through all the changed state objects to find ones that we actually created from the database. We don't care about the other ones. Then we're going to launch a coroutine on the I/O dispatcher because we're about to do some blocking I/O. We're going to take a child snapshot of the snapshot that was applied. And the reason we take a nested snapshot of that particular snapshot is so that if anything changed between the time when this callback was invoked and this coroutine got dispatched, we ignore those changes and we only look at the actual changes that we know were applied, because those are the ones that we calculated this change DB states from. So we need this consistency. And so now we've created a read-only snapshot that's a child of the one that these changes were applied to. We're going to enter the snapshot, and we're going to then loop over all the changes and just write them to the database. And lastly, we have to dispose the snapshot just to avoid memory leaks. So yeah, again, I don't know if this would, I went backwards there. I don't know if this would actually work, but if anyone tries this, I'd be really curious to hear if it did. And kind of to tie it together, one way you might use this, you can call observe user as state, get that state object, and then just read the name, and to update the database, you just write to the state object. And when that next snapshot is applied, it'll kick off that logic we just saw and update the database. I have no idea if this would work, but it might be cool to experiment with. So there's all kinds of cool stuff you can do when you actually get into the kind of workings of snapshots. I'm almost out of time here. So if you remember nothing else from this talk, just think of snapshots as Git for your variables. Hopefully, if you want to learn more, you can kind of dig into the code, and at least you'll kind of have some idea at a high level what's going on. You can also check out some of these links. I wrote a blog a while back with a bit more of a detailed walkthrough about creating custom state objects. So that's here. And then this algorithm that we talked about for the snapshot IDs, it's actually not just a snapshot thing. It's an algorithm called multi-version concurrency control. And if you've ever used a database, you've probably used this. Most databases use this behind the scenes. And some version control systems do too. So if you want to read the academic paper, it's there. And the slides are also available. I've got 40 seconds left, so if you have any questions, feel free to tweet. I could maybe take one question now really quick, if anyone has a question. Otherwise, feel free to grab me after the talk. And yeah, that's it. Thanks.